Hello everyone and welcome back to another video. In this video, I just wanted to finish up the section of the textbook that we were working on in the previous video of this series titled Greatest Common Divisors and Linear Diophantine Equations. So with that, let's just jump right into the math. So if you recall, at the end of the last video, we were looking into a lot of theorems regarding this linear Diophantine equation. And that equation is ax plus by equals c. And what a Diophantine equation is just an equation that we seek integer solutions to. So in our case, we're concerned about the solutions x and y when we have three integers a, b, and c. And we're concerned about what sort of situations these values have solutions. What are the properties of a, b, and c in that case? What is the relationship between them? If you remember in the last video, we saw that if the GCD of a and b equals 1, then the equation where c is 1 has a solution. Has a solution x and y here. And I think this allowed us to prove many different useful theorems, as we saw in the last video. Just kind of for a warm-up on this, let's look at one theorem that we didn't prove in the last video, just to remember kind of how we use this in our proofs. So we'll look at theorem 1.45. And this theorem is as follows. Let a, b, and c, let a, b, c, and n be integers with n greater than 0 if AC is congruent to BC mod n, then, not yet, hold up. And the GCD of C and N equals 1, then A is congruent to B mod n. So if you remember before when we were talking about congruence, you might remember that this relationship isn't always true. If A times C is congruent to BC mod n, that doesn't always mean that A is congruent to B mod n. However, what's important about this theorem is that we add the fact that C and N are relatively prime, and then that allows this relationship to work. So what we're going to do is show how this is possible. Let's go in and improve this. So for our proof, we're going to let a, b, c, and n all be integers. With n greater than 0. A congruent to, or AC congruent to BC mod n, and GCD of C and N equal to 1. Okay, now that we got those assumptions out of the way, this is a C here. It might be a little hard to see, but hopefully you guys can all see that. So then, by the definition of congruence, N divides AC minus BC. So AC minus BC equals ND for some D contained within the set of all integers. So based on this, by theorem 1.39 from before, 1 equals c x plus ny for some xy integers. And then based on this, we can do a bunch of algebra that I'm going to go through quick. So thus, because what we're interested in proving is that A is congruent to B mod n, so we're going to look at A minus B, and if we can show that n divides it, then we've shown what we're trying to prove. So AB equals A minus B times 1, which equals A minus B times CX plus NY, which then equals CX A minus B plus NY A minus B. So then we'll just continue on the next line. AB equals that. So then we can continue it by taking this X, AC minus BC plus NY A minus B, which equals X. And remember from before, AC minus BC equals ND, XND plus NY A minus B, which equals N XD plus Y A minus B. So this means, hence, N divides A minus B. So A is congruent to B mod N. And that is a very useful result because it means that when we know C and N are relatively prime, we can take out that C and just be left with A being congruent to B mod N. So you can see here how useful this particular identity is here. So with that, let's kind of look into this Diophantine equation a little bit more. So in the last video, we showed that if A and B are relatively prime, that means that this equation has solutions. We have solutions. We also showed that if A, B is equal to C for any integer, that means that ax plus by equals C. But notice here that we prove the alternate direction for in this case. We can show that if this equation has solutions, that means that the GCD of A and B is equal to 1. That's not true of this this equation right here. Just because it has solutions x and y such that we can get the greatest common divisor, so that we can get C, that doesn't always mean that the greatest common divisor of A and B is C. But what does this tell us? What does it tell us if we can get solutions to this equation for C? And that's what we're going to start to look into in this video. And what it turns out to be the case is that if we can show that there's solutions here to this equation for C, that means that the greatest common divisor of A and B divides C. So let's go ahead and prove that. We're going to look into it right here. I should have room, hopefully. 1.48. And this theorem basically states that given integers A, B, C with A and B not both 0, there exist integers x and y such that ax plus by equals c, and then that satisfy the equation ax plus by equals c if and only if, so we're showing a biconditional here, the greatest common divisor of a and b divides c. Okay, so let's go in and prove this. So with a biconditional proof, remember we have to prove each direction. So we're going to start by proving the forward direction. So we're going to suppose a, b, and c are all integers with a and b not both 0. And ax plus by equals c for some x, y that are integers. Okay, so we have that. Now what we're going to try to prove, so we're going to start by let the GCD of a and b, let's just write it in a short form. Let the GCD of a and b equal d, and we're just doing this for the sake of having something to denote it, so I don't have to write that out every single time. So d divides a and d divides b. Hence, dk equals a and dl equals b for some k and l that are integers. Thus, now we can say something about c. C equals ax plus by, as we know, which also equals dkx plus dly. So we know we can factor out this d and be left with kx plus ly. That almost looks like an x. Don't worry, that is a y. So AB, the GCD of A and B divides C. Okay, so we've proven the first direction. Relatively quick proof, actually, for such a important concept. But I think we did a lot of the work. A lot of the work earlier on is kind of about getting to this equation. But I guess this one is relatively straightforward, just because we know that A and B divide it. But this other direction, we're going to get a lot of work done by the theorem that we proved in the previous video. So we're going to suppose A, B, C are all integers. With A and B not both 0. And GCD A and B dividing C. Okay, so we're going to start here, and now we're going to try to find integers that exist such that ax plus by equals c. All right. So what we'll do, again, we're going to let d equal the GCD of A and B. So dz equals c for dz equals c for some z in the set of all integers. So by theorem 1.40, let's just write it out. Am plus bn equals d for some m n that are integers. Hence, c, which we know equals dz, equals am plus bn times z, which equals amz plus bnz. Thus, we can finish it up. Ax plus by equals c, where x equals mz and y equals nz. Sweet. And now we have the proof. So what we've done is we've shown what when we know that we have solutions to ax plus by equals c, what does that say about c? Well, it says that it is some multiple of the greatest common divisor of a and b. So now we kind of have a basic understanding of what sort of circumstances ensure that ax plus by equals c has a solution. However, now what we're left with is a question of how we can actually generate these solutions. And that's where the Euclidean algorithm is helpful. So we'll see how that is, because using the Euclidean algorithm, we can generate one solution. And then what we're going to do next is show how we can generate other solutions and ultimately show some type of theorem that can give us the set of all solutions to a linear Diophantine equation once we have one solution. Okay, so what we're going to do now, we're going to start by showing how the Euclidean algorithm can give us one solution. So what you might remember from the last video, I think we gave potentially this example. This is an example from the textbook, but what this example shows us is when we have a equals 51, b equals 15, and then we'll say that c equals 3 times the GCD of 51 and 15. And first we're going to go through and figure out what the GCD actually is. So remember how we do this using the Euclidean algorithm. You just apply the division algorithm over and over again. So 15 equals 2 times 6 plus 3, and then 6 equals 2 times 3 plus 0. So then we'll have the GCD of 51 and 15 equals 3. So C is going to be 9 here. Okay, so once we have that, we can work backwards to write the GCD in terms of A and B. So using this equation, we have the GCD in terms of 6 and 15, and then we have 6 in terms of 15 and 51. So the way that this works, you'll see, I guess I'll just walk you through it, how to work backwards from here. So 15 equals 2 times 6 plus 3, but 6 equals 51 minus 3 times 15. So what we can do is plug in 15 equals 2 times 51 minus 3 times 15, and then add 3, of course. And this means that we have 2 times 51 minus 6 times 15 plus 3. And then this gives us 3 equals 7 times 15 minus 2 times 51. So if we want to get to C, all we need to do is apply a scalar to both sides. So what we have is 9 equals 3 times 7 is 21 times 15 minus 2 times 3 is 6 times 51. So what we have, if we're going to write this out as C, or as ax plus by equals c. The way that we can do this, remember, a is 51, b is 15, c is 3 times our GCD. So we have a is 51, x is -6, b is 15, y is 21, and then c is 9. And then if we go and plug this into a calculator, we should be able to see that this should work. I did check this earlier, so if this doesn't work, I'm actually going to be very surprised. But let's just do this live. 21 times 15 minus 6 times 51. And what we see is that it equals 9 like we'd expect. However, there's also other solutions to this equation. For example, one simpler solution could be 4 times 15 minus 1 times 51. And that's just 9. Another solution that's a little more complicated could be, for example, 38 times 15 minus 11 times 51. So what we can see is that this solution that we get from the Euclidean algorithm is not unique. There's other solutions here with different integers. How can we come up with these other solutions? Well, we will also have a theorem for that. So this theorem is theorem 1.53, and what it states is that let a, b, c, x, y, here. I'm going to write a 0 here, so it's x naught, y naught, be integers, a and b not both 0, like usual. And then this theorem is going to have two parts. The first part that we're going to prove is that if x equals x naught and, or let's just add a comma for space reasons, and y equals y naught, is an integer solution to ax plus by equals c, then for every integer k, the numbers x equals x naught plus kb over the GCD of a and b, and y equals y naught minus ka over a b over the GCD of a and b are also integers that satisfy that Diophantine equation. Okay, so this will be the first thing that we prove. So we're going to prove that this algorithm can get us another pair of integers that satisfy it. And then the next thing that we're going to prove, moreover, every solution to the linear Diophantine equation is, or we'll write it out again because that's the way they write it on the book is like that. I usually try to write these theorems word for word from the book. Ax plus by equals c is of this form. And when it says this form, it namely specifically means it's the initial solution plus some multiple of b over the GCD of a and b, and then the other one is is the first solution that we found minus that same k, that same integer, times a over the GCD of a and b. So this shows that this form gives us all of the solutions to this linear Diophantine equation. So let's go through and prove this. So for the first part, we're just going to prove that this gives us a solution. So all we're going to do is basically plug in this formula and see that it still gives us c. So what we're going to do, and I'm going to write this as one kind of continuous proof, but I'm going to number it 1 and 2 just so you guys can kind of follow where we're at in the proof. So we're going to let a, b, c, x naught, y naught all be integers with a and b not both 0 and c equals ax plus by 0. And then we're also going to let k just be some integer. Then a times x naught plus kb over ab plus b times y naught plus, or sorry, not plus, it's minus this time. So then we're going to take that, subtract off k a minus GCD of a and b again. And then this is going to equal a x naught plus k a b over a b plus b y naught minus k a b GCD of a and b. So what you'll see is that these cancel out, and then what we're left with is a x naught plus b y naught, and that just equals c. So we've proved that first part. So basically what we've proved is that this formula in the theorem gives us another pair of integers that still equals c. Now the next thing that we're going to show is that every single integer that satisfies this Diophantine equation is of this form, one of the solutions plus k times b over GCD, and that solution's y coordinate minus ka divided by GCD of a and b. Now this first part was a lot shorter, but this part's going to be a little bit longer, and the way that I'm going to approach it is by basically feeding in some random solution. We're going to call it x prime y prime, and saying that it works, and then we're going to prove that it must follow that form. If it is a solution, it must follow that form, is basically what we're proving. So we're going to let x prime y prime be integers that satisfy the linear Diophantine equation. Plus by prime equals c. And then this is going to come in handy later, but what I'm going to do now is just say, without loss of generality, a does not equal 0, because we know one of them is not 0. So basically we can assume that a is not 0, and if b happens to be the one that's not 0 and a is 0, then we can just switch which one we're labeling a and b. So without loss of generality works here for that reason. This proof would be symmetric either way. So without loss of generality, A is not equal to 0. So thus, ax prime plus by prime equals ax naught plus by naught, because both are equal to c. So a x prime minus x naught plus by prime minus y naught equals 0. And this is just doing some rearranging, just to put it in this simpler form. So now we're going to let D equal the GCD of A and B. So D divides A and D divides B, which means actually we'll put this on a different line, sorry. Hence A equals dP and B equals dQ for some PQ integers. Okay, therefore what we're going to do some algebra here. 0 equals ax prime minus x naught plus by prime minus y naught equals dp x prime minus x naught plus dq y prime minus y naught which equals dp x prime minus x naught plus q y prime minus y naught. And since d is not 0, we know that d is not 0 is because the greatest common divisor of every single pair of integers is always going to be greater than or equal to 1. So we know d isn't 0. And because of that, the product of this must be 0. So one of these two must be 0. That means since d is not 0, the other one must be 0. So this means 0 equals p q or x prime minus x naught plus q y prime minus y naught. Okay. And because of that, what we can do is say p q prime minus x naught equals negative q y prime minus y naught, meaning p divides negative q y prime minus y naught. Okay, so we know p divides q y prime minus y naught. Now, by our favorite theorem, theorem 1.40, d, which remember was the greatest common divisor, equals am plus bn, which equals dp I got a almost time to restart thing, so hopefully this is still okay. dpm plus dqn, which equals d times p times pm plus qn for some m n that are integers. So that's theorem 1.40 basically says the greatest common divisor is equal to am plus bn for some mn that are integers, and then all I did was do some algebra to get that d out. So since d is not 0 and d times 1 equals d times pm plus qn, 1 equals pm plus qn. And remember, if we can write that linear Diophantine equation of 1 equals p times x plus q times y, if we have solutions to that, which we do here, m and n, that means that the GCD of p and q is 1. So we know that p and q are relatively prime. And that's by theorem 1.39. Okay. So now we have that. So we have this fact that p divides negative q times y prime minus y naught, and we have that the GCD of p and q equals 1. And that means that by theorem, which we proved in the last video, theorem 1.41, we know that p divides negative y prime minus y naught. So pk equals negative y prime minus y naught, or that's just y naught minus y prime for some k. And now from here, here we're going to want to remember what p actually represents. And remember that what p is, when we defined it earlier, is just a divided by the GCD of a and b. So what we're going to do now is use that formula more specifically, because that's the way that it's written up here, and see what we can pull out of this particular relationship. So y prime equals y naught minus pk, which also equals y naught minus p, which is, so it's a, or ka, over the GCD of a and b. So we're getting somewhere. We're getting very close, actually. We've shown now that if y is also a solution to this linear Diophantine equation, it must be of the form y naught minus ka over the GCD of a and b. We've shown that now, so that works. So we're doing good. We also know, so let's go back and we can plug this in to this equation from earlier where we have a and b both together. Hence, equals a x. Here, let me make sure that my thing doesn't restart. X prime. I schedule the restart. I will schedule it for way later today. Yeah. Okay. Let's just do it tomorrow. Why not? Okay. Sorry about that. Very weird technical difficulties. Sometimes the computer wants to do this weird stuff, so I'm just going to not let it. So we can expand this, and what we're going to do is plug in the equation that we got for y prime into our equation from before. So y prime, remember, is y naught minus ka over a minus b minus y naught. And now we can go to the next line. So 0 equals a x prime minus x naught minus, so these two terms cancel, minus KAB over GCD of A and B, which also equals A times x prime minus x naught minus KB over GCD of A and B. Now, remember, before we assume that without loss of generality, A is not equal to 0. We just need one of these to not be equal to 0 to make this next step work. So if you wanted to go back before, all you'd have to do is switch A and B, and the argument would be symmetrical. But we'll do it for, since A does not equal 0 now, since A does not equal 0, 0 equals x prime minus x naught minus KB over the GCD of A and B. And because of that, we know, so x prime equals x naught plus KB over GCD of A and B. And that is what we were trying to prove. Hence, all solutions, because remember, we just chose a random solution. It was just a general solution. It could be anything, but we showed that it has to follow this form, x naught plus KB over GCD of A and B, and y naught minus KA over the GCD of A and B. And there we go. That is the proof. So this was a bit of a longer proof. But if we go back to before, what we can see is that the solutions x and y, there's more than just this particular solution. So remember before we also showed that x equals -1 and y equals 4 as a solution. Now using these, we can see, so let's scroll down here. We see that what we can do to x is add KB over GCD of A and B. So in this case, B would be 15. 15 over 3 is, so B over GCD of A and B. Here is 15 over 3. And then A over GCD of A and B. Here is 51 over 3. And then 51 over 3 should be 17. 15 over 3 should be 5. So what we'll see is that all solutions to this equation follow the form -1 plus 5k and y equals 4 minus 17k. So if we want to see how we got our solution from before, let's plug in k is equal to -1. So x is equal to -1 plus 5 times -1, and that's just equal to -6. So we have that particular solution, and then y equals 4 minus 17 times -1. 17 times -1, or -17 times -1 is just positive 17. 17 plus 4 equals 21. So we can see that all of the solutions to this particular equation, 51 plus 15y equals 9, they all have to follow this form. This form gives us every single solution to this equation. And that's why this ends up being helpful. So if we have an equation of this form, we can always just use this type of algorithm to find every single solution to that equation. Okay. So with that is what we have for, that's it for the Diophantine equations and for GCDs and those connections. Next, we're going to move into the topic of least common multiples, which is another concept that you may remember from elementary school. But I think what the purpose of number theory kind of is to take some of these ideas that we learned in elementary school and prove them. Just go in, rigorously show why they're justified. And that's what makes this more of higher level math. Because some of the individual topics that we can talk about can be very basic and seem rudimentary, but when we actually go in and prove them, we have a firm foundation for why these things are true. And then we can use the different concepts that we prove to prove things from more advanced topics. For example, like cryptography is a very common application of number theory that we're going to get into a lot later in this series. There's also a lot of things with primes. I think cryptography tends to be one of the most practically used examples of number theory, but there's also so much more depth and complexity to number theory that we get into once we get past a lot of these foundations, where we're kind of just proving things that we already know, or they might be concepts that we're already familiar with. But as we get further, we start to go a little bit deeper. Okay, so to go into this concept, we're going to talk about the least common multiples. So this section, the definition, definition the least common multiple of two natural numbers a and b denoted least common multiple of a and b is an integer m such that a divides m, b divides m, and if a divides c and b divides c for some integer c, then m is less than or equal to c. So this is a very similar type of definition to what we showed for the greatest common divisor. We'll see that it's a common multiple of a and b, a divides m, b divides m, but then also if there's some other thing some other multiple of a and b, then the least common multiple is smaller than it. So very intuitive definition, but I wanted to write it out formally just so we get a basic understanding of how we can do stuff in proofs with this. So let's start by proving. We're going to prove one theorem about this and then one corollary that pretty much immediately follows. But for this theorem, what we'll show, sorry, one second. Theorem 1.57, and this theorem states if a and b are natural numbers, then GCD of A and B times least common multiple A and B equals A times B. So our proof is, so that's basically what we're going to try to prove. If we have the GCD of A and B multiplied by the least common multiple, we'll always just get the product as just the product of A and B. So let's go ahead and prove this. So to prove this, we're going to let A and B be integers, and we're going to denote D as the GCD and M is the least common multiple. Okay, from there, we're going to let, D divides A, so we know that D obviously divides AB by theorem 1.6. Hence, dm prime equals AB for some m prime that's an integer. So my goal here is going to be to try to show that m prime is the least common multiple. Because once we can show that, then we have the greatest common divisor times the least common multiple just equals AB. So what we're going to do is write out this the greatest common divisor in a form that we can use more algebraically. Since D divides A and D divides B, A equals dP and B equals dQ for some PQ integers. Okay, thus dm prime equals AB, which equals dBp. So since, dPb. So since D does not equal 0, m prime equals PB, meaning B divides m prime. And then a symmetric argument will basically show that A divides m prime. All we'd have to do is substitute in dq in for B, and then we'd have A dq. Since D is not 0, m would be equal to, or m prime would be equal to q times A, which would mean that A divides m prime. So symmetric argument. A divides m prime. So that means that m prime is a common multiple of A and B. Now we want to show that it's the least common multiple of A and B. So we're going to let n be some other common multiple. So n is going to be an integer such that A divides n and B divides n. I'm also going to say that n is greater than 0. Because we don't really care about the negatives in this context. So n equals AK and n equals BL for some KL integers. Okay. By theorem 1.40, ax plus by equals d for some integers x and y. So nd equals n times ax plus by, which equals nax plus nby. And then we're going to keep expanding this, so it's going to be blax plus ak by. So continuing it, nd equals ab lx plus ky, which means that it equals dm prime times lx plus ky. And using this principle again, since d is not 0, because the greatest common divisor has to be greater than or equal to 1, n equals m prime times l x plus ky. So m prime divides n. Hence, since both these are positive, m prime is less than or equal to n. Therefore, m prime equals the least common multiple of a and b. So it equals m. Thus, ab equals dm prime equals dm equals GCD of a and b times the least common multiple of a and b. And there's our proof. Okay, so that's our next proof. Also, one point I guess to make, when we're looking at this, when we're seeing like it divides, a divides c and b divides c for some c that's a integer, it might be more proper to say that this is a natural number here, because technically c could be below the least common multiple if c is negative. So that's maybe a technical issue here, so maybe I should have potentially wrote this a little bit differently. I just caught this now in my notes. Yeah, I caught this while I was writing the proof, but in my notes I just didn't think about that because it's not that important. But what's key here is that it is a natural, because technically if we wanted to be super precise, that's how we would write this. And then a similar thing here, so it would be n is in the naturals, but I basically fixed that by saying with n greater than 0. But that's a more minor point, more nuanced. But just for precision, I just wanted to clear that up. And then, okay, so from here, what we're going to get is a corollary. And this will be a very quick proof, hopefully. If a and b are naturals, then the least common multiple, a and b, equals ab if and only if a and b are relatively prime. Or in other words, if we wanted to really write this out, i.e. GCD of a and b is 1. Okay, so our proof, we're going to start, we're just going to let a and b be naturals. And then for the first direction, we're going to let, because we're doing a biconditional here, so let least common multiple of a and b equal AB. Then by theorem 1.57, GCD of A and B times least common multiple of A and B equals AB. So AB equals AB times GCD of A and B. And since A, B are not zero, they're natural numbers, they can never multiply together and make zero. The GCD of A and B is 1. Okay, so that's our first direction, and then the second direction will also be relatively quick. Let GCD of A and B equal 1. Then by theorem 1.57, GCD of A and B times LCM of A and B equals AB. So AB equals 1 times least common multiple of A and B, which just equals least common multiple of A and B. And that is the proof. And with that, we are done with today's episode. Look at us. Look at all our proofs. Amazing. Incredible. Wonderful. We are incredible provers. So yeah, that's all that I have for this section. And this is actually the end of chapter 1 of Number Theory Through Inquiry, which is the textbook that I'm going through. You can find the link for that in the description below if you want to follow along. But this is the end of chapter 1. So thank you all for getting through this first chapter with me. Next, we're going to go into prime numbers, looking into proving the fundamental theorem of arithmetic, and into like how many prime numbers there are. Spoiler alert, there's infinitely many. So what we're going to do is go through, we're going to prove all of that. Going to be super fun. And as we keep going, we're going to keep getting a little bit more complex, a little bit more abstract. The proofs might get more complicated, but the nice thing is now we have this very important foundation with everything that we have in chapter 1. So we're going to reference these theorems all the time. We're going to keep using them over and over again, especially that theorem 1.4 or 1.40. We've already seen how useful it can be for proving all these different things. So yeah, we're going to keep using that going forward, but I really hope you guys are enjoying this content. This stuff is definitely more of a selfish product for me. I really enjoy making the math videos. I enjoy kind of refreshing my learning on this stuff, but I really do hope you guys enjoy it. And yeah, tune in next month. We're going to start the chapter on prime numbers, chapter 2. And if you like the video, go like it. If you really like it and want to keep getting notified of uploads, there's a subscribe button down there. I also have a Patreon that you can go to and support if you would like. I also have a Discord. Pretty dead right now. An occasional troll pops by and just posts whatever nonsense they want to. But it'd be cool to build a community there. If you have any questions about the math, there should be a dedicated math section. But yeah, thank you all for watching, and I hope to see you all in the next video. Peace.